Hi, it's Mr. Yeager again. We're continuing our optics unit. This time we're finally moving on away from mirrors and looking now at the process of refraction, how light will refract between two different substances. All right, looking at refraction. We already, in this particular section, I'm going to review what refraction is, a couple different concepts of what will happen when light travels from one density medium to another. We're going to figure out which way that the line should be drawn, how it's drawn, and why is that occurring. In addition, we will look at an interesting property called total internal reflection, but this is all going to be very conceptual. I'll introduce a couple formulas, but we're not going to use them. We're actually not going to calculate them at all. We just have to kind of understand what their purpose is more than anything else. So here we go. So going with refraction. All right. In terms of refraction, again, going back to even the wave unit, this is the bending of light as the light, or as the wave, but in this case light, as it travels through to a new medium. A new medium, and specifically with a new density. Obviously, if it's a new medium, it should probably have a new density anyway, but we're going to be very, very clear about that. So the bending of light as it travels from one density to another. Before, when we talked about this very briefly, basically what you have is the light comes in. All right, we'll talk about this normal line. We'll draw these all out. And either the light will bend toward the normal, or it could possibly bend away from the normal. All right, and we're going to talk about when would each one occur and why. Okay, if it doesn't change to a new medium, obviously that light wants to keep on going perfectly straight. It would like to go perfectly straight. All right, so the first big thing is, which way will it bend? Okay, so if I want to go from high density to low density. High to low density. Okay? High to low density. All right? Usually you're going to see this drawn out either in a vertical way or horizontal way, so we have to be able to do both. The way to best do this is basically denote two boundaries. Create a barrier of high density and a barrier of low density. I mean, this can be, you know, it might be looking kind of weird. Basically, what water, when light travels from water out into air, okay? High density to low density. We want to draw a normal line on that, basically a perpendicular line to the surface, all right? For high to low density, when the light comes in, the incident ray comes in, always draw like basically going to that intersection of barrier and normal line. As it comes in, as it goes from high to low density, it will bend away from the normal. So high to low density, light will always bend away from the normal. Away from the normal line. All right? The way I try to describe this is it's basically like the idea that essentially the higher density is thicker. Think of it like almost as a thickness. And essentially think of it like as a car coming out, its wheels get stuck a little bit more on the high density, and you basically peel back toward the higher density, but you come out onto the road. Okay? That's what I'm trying to say. It's basically almost like it's a little more sticky in the high density, and so it pulls you back toward the high density some, but obviously you're now in the low density area. Okay? Excuse me. So that's high to low. If I go low to high density, as light travels from low to high density, again, this would be air to water. Normal line. Incident ray comes in, it will bend toward the normal. I'm going to say refract. Let's use the word. Refract toward the normal. Okay? The greater the difference in densities, the greater the refraction will occur. All right? The greater the change in densities, the greater the refraction that actually does occur. So the greater the difference between these two, the more it will bend closer and closer and closer to the normal line itself. All right. So that's another way to basically think about this. All right. So a question might be, why is the light even bending? Okay. It's not, like I said, the stickiness factor or anything like that. Okay. Why does light travel? Why does it bend as it travels through one substance to another substance? All right. And basically, this is related to what's called a substance's index of refraction. An index of refraction, which I denote, or we denote as N. All right. So first off, this index of refraction is a property of the matter. Okay. All different substances have a different index of refraction. What it's basically telling you, all right, is it's going to tell you how much refraction will occur. All right, how much refraction will occur. Specifically, the formula is the index of refraction, N, is equal to the speed of light divided by the velocity, speed of light in a vacuum. Let me be more specific. The speed of light in a vacuum divided by the speed of light in the medium. All right? So speed of light in a vacuum divided by the speed of light in a medium. We could actually go ahead and solve these problems. You'd need the numbers, but basically the speed of light in a vacuum, all right, actually the symbols for this is C over V. This is another way we write it. C is the speed of light, V is the speed in the different medium. All right? So it's a ratio. Again, no units or anything. It's just a number. All right? And so what we can see here is the speed of light in a vacuum, that is a constant. Okay, the speed of light in a vacuum is 3 times 10 to the 8th meters per second. All right, that's how fast light is through space. All right, that's essentially how fast it is through air, but technically it's slightly slower, but not enough for us to really measure any difference. But when you travel into water, the velocity decreases. As you go to a higher density medium, all right, you will decrease the velocity of light. You will decrease the velocity of the light itself. All right, it's more difficult for it to manipulate itself through the substance. All right, again, this change is minimal. All right, but it is actually measurable as well. All right, and so what we have here is there's a bunch of different objects that have different indices of refraction. All right, basically, all I want to tell you is air has an index of refraction of 1. All right, because there really is no difference in the speed of light in air versus a vacuum. All right. Other objects, water, I don't have a specific one. Its N would be greater than 1. Okay. And so what we're basically saying is, as you increase N, the index of refraction, you're increasing the density of the object. All right. N is directly related to the density. So the way that you might see a problem would be something like this, where I say you have a drawing on your test, and you have light. It's traveling from n equals 2 to n equals 3. And you might sit there and go, wait, what? What does this mean? And the question is, will it bend toward or away from the normal? Well, what you need to think is okay, what does index of refraction mean? If I have a higher index of refraction, which is 3, this is higher density. Higher density. This is lower density. So this is light traveling from something that is lower density to higher density, and so it should bend toward the normal. So that would be a question you might see. Okay. So that's all we're going to use with it. You're never going to have to calculate an index of refraction in this class. All right. Just so that you see it as well, and we mention it. To specifically find how much the light will bend, we use something called Snells Law. All right. So again, this is going to describe the angle. The angle the light bends through the substances. Okay. The light refracts And the formula here is all right. The index of refraction of the first substance times the angle that the light comes in, the angle that it comes in related to the normal. Okay, all angles are related to the normal. I'm struggling. To the normal will equal the index of refraction times the sine of the angle that it comes through the second medium in relation to the normal. All right. So what we're talking about by that is, if I have light come on in and it refracts, what we're saying is this is N1, this is theta 1. This is N2, this is theta 2. From underneath. All angles are related to the normal line. Again, we are not going to get in that much more detail. We're not even going to calculate this, but it's something that if you go to a higher level physics class in college or so anywhere else, you probably will start using this formula as well to help you find how much the light actually does bend between the two substances, okay? And the hard part I think a lot of people miss is that angle is related to the normal line, not with the boundary, okay? So that is the main ideas with refraction, of how it will bend from one substance to another, okay? So we have a very interesting thing that can happen in a very particular situation, and that we're going to call that total internal reflection. So you're sitting there going, all right, back to reflection, this must be mirrors. It's not. This is very much related to refraction, okay? So if you think back to an example that we were doing, all right, let's say I'm going from high density to low density, all right? I'm coming from water and the light's coming back out, okay, into air. I have my normal line. We said if light is leaving the higher density and going to the lower density, it should bend away from the normal. And the more extreme that I come in, the greater the angle that I basically come in, the closer it's going to bend right along the boundary line. So what happens if I come in at an angle so extreme where there's no more space to bend? What happens at that? Okay, I'll draw that a different color. What if I come in at this angle where if I try to bend it anymore, it's going to be on the flat line? Okay, well, that's basically what happens. It will refract right along the surface. All right, and what happens if I go even higher than that? It actually will reflect back in. All right. And so this occurs, the orange situation here, the orange arrow, is illustrating this idea of total internal reflection. All right? What happens is light no longer escapes. This is why it's possible that you might not see somebody that's underwater for a moment, depending on the angle that you're looking at them. The light might be exactly refracting along the surface, and it never reaches your eye, and you don't see them. It looks like they disappear for a moment. All right? This is also what's used in fiber optic cables to help produce very, very fast, obviously light speed signals, especially for internet signals and so forth, and TV signals. We are using these to allow it to travel very quickly, and none of it escapes. Okay, it's going very, very fast. So there's a couple key things about total internal reflection. First off, you have to light has to be traveling from high to low density. That's key number one. It will never work with if you go from low to high density. Okay, it will never work because that light wants to go through. I mean, the more extreme you get, basically, the more straight line it goes. The more, it will bend more and more toward that normal line. Okay. What has to happen is we reach something called a critical angle. And I'll go back to my drawing and show you the critical angle. So this would be called theta C. The critical angle is the angle when the light refracts on the boundary. So that would be the red line that I have here. This angle from the normal line, this angle would be called the critical angle. The critical angle. All right? At the critical angle, it's not reflecting yet. It's still refracting, but refracting on the boundary, on the surface between the two sections. And so, I'm going to need to erase this just to have a little bit of space. I'll draw it out one more time. Okay. So, I'll go red. If light comes in higher than the critical angle, it will be reflected. It will be reflected. Okay? And it will be reflected back into the higher density substance. That is total internal reflection. All right? So draw it out one more time. Basically what we have here is light has to be traveling. And again, don't be confused. I always, whatever reason, when I do these examples, I always start from the bottom, because I always think of water below and air above. All right? We have a particular critical angle. I'm going to denote this again in red. This is the critical angle. At the critical angle, light will refract right on the boundary, right along the boundary. It doesn't escape, but it doesn't get reflected back in. If you come in below the critical angle, again, the angle is measured from the normal. Below the critical angle, it will refract through. It will go through to the new substance, but bend away from the normal. If I come in higher than the critical angle, it will reflect exactly back. All right, it'll follow the law of reflection. If it comes in at that angle, it'll reflect back at that angle. Again, as long as the surface is smooth, which we're going to assume it would be. Okay, so that is total internal reflection. All right, so last thing I want to cover in this particular section is what device, what object will refract light. All right, what object will refract light? That is lenses. Lenses is an instrument that refracts light. All right, and we have two types out there. All right, we have two types. The first one is convex. All right, we have a convex lens, and it looks like this. It's one where the center of the lens is thicker, is wider than the edges of the lens. Okay, and so what happens with this type of lens is, now this time it's not a mirror. The light will come in, and when it comes through the center of the lens, or through the lens itself, it will refract. And the real light, this is all going to be big when we start doing the lens diagrams, the real light refracts through to the other side, and it will refract through, again, a focal point. So the real light is now traveling through. So we think about that, especially when we start doing the positive DI and the negative DI again. We follow the real light, which means on these diagrams, the right-hand side will be positive DI. Real images will be formed on the right-hand side. Okay, it's being created by real light. So the focal point for convex lens is on the opposite side of the lens, and that is on the positive side. Light will travel and basically refract and bend through that focal point. Okay, so that is what the convex lens will do and look like as we start moving to lens diagrams, lens ray diagrams. So that's convex, thicker in the middle, and then this is also called a converging lens, just like we said with the mirror. We don't use that with the mirrors too much. We definitely use it with lenses, a converging lens, because all the light is converging to a single point. All right. The other type, well, guess what? It's called concave. Concave is thinner in the middle. It's thinner right through the middle. All right. Obviously, if we get confused, you cave in. You're entering the cave. You have the entrance of the cave there. This is also called a diverging lens, because what's going to happen here is the light's going to hit, and it's going to go out. What does it go out to? Well, that goes with the focal point on the in front of the lens. So the real light goes on the opposite side of the focal point. So you can see for concave lens, it's going to have a negative focal length. Convex, it's going to be positive focal length. but all the light gets diverted, right? Diverted, okay? It'll bend away. Obviously, if it goes through the middle, it'll go straight, that's fine. Anything away, it gets diverted out. So that is how a concave lens will work, all right? And that's where we're going to end for today. All right. So just a couple terms of what is refraction. Make sure you understand which way the light should refract when it enters different mediums, different density mediums. What is total internal reflection, and just what does a convex and concave lens look like, as well as what will the light rays do as they travel through. All right. So that's it for this one.